So, let's go ahead and get into this. All right, radiography. Radiography is a branch of science, and it's a branch of science under the umbrella of medicine, right? So, medicine, modern medicine, is a branch of science. What makes medicine and radiography a part of science is that things that we do are objective. They're based in fact. That's what it means to be objective. We make observable changes. We make observable, everything we do is observable, right? Detectable by the human senses. We can see the radiographs that we make. And our knowledge is demonstratable. I can show you how to do everything we do, right? Everything's quantifiable, demonstratable, observable, and based in fact. So that's going to differentiate science from other things, for example, that clearly differentiates science from other endeavors such as religion, right? Or philosophy, for example, which we don't have to base things in fact. We can base things on things like belief, right? Science is purely based on observable fact. Okay, so things that make science special are sort of the process, right? So the scientific process is what makes science different than other things that we do, other endeavors that we approach. All right, so one of the first things that makes science different than other things, and this is pretty much the idea of thinking logically, right? Logical thinking. So this is an idea called parsimony. Okay, so I'm trying to show right now what science is, how science approaches things. Okay, so any question that you want to ask about the world, right? For the simplest question, not even really scientific, like you hear a knock at your door, open your door, and there's a pizza at your door, right? What's the most likely explanation for somebody showing up to your door with pizza? You ordered the pizza, right? You could think of and conjure up all sorts of unlikely explanations, right? Like somebody accidentally ordered you a pizza, right? Or, it just happened that that pizza man stopped at the wrong house and delivers you a pizza, right? But the point is, you can think up all sorts of complicated answers to any question you want to ask, right? How did such and such thing happen? How did the universe happen, right? It's a complicated question, but you can think of it with simple things. Why is this pizza at my door tonight, right? The simple explanation, out of all the possible explanations for why something is the way that it is more likely to be true than the more complex or elaborate explanations for things. Okay, so if you can think up many ways something could have happened, and lay them all out, it could have happened this simple way, it could have happened these very complicated ways. The simple way that things happen is just the more likely way. Okay, there was a man named William of Ockham, sometimes said, and he's credited with this idea of something called Occam's razor. He didn't call it Occam's razor; it was called that about 100 years after he died. But the idea is, what do razors do? Shave, right? Shave things away. So the idea is, take whatever question you want to ask, take all of the complex ways that it could be answered, and try to shave away all the unnecessary baloney, all the unnecessary nonsense from your possible answer, and you'll end up with the simplest possible answer. Okay, and the idea is that the simplest possible answer is just more likely to be the right one. So when science asks a question about the world, it's going to need to be able to answer that question, right? And you can think of many explanations for things, and it's just overwhelmingly likely that the simple explanation is more likely to be the right one. It doesn't mean that the simple explanation will end up being the right one. It's just that science lends more of its credence, more of its belief into saying that the simple answer is probably going to be the one that's going to be right. For dating purposes, Willem of Ockham, 1285 to 1347. So he was Middle Ages, he was one of those dark age, medieval times philosophers. One of the very first, and one of the most well known from those early times.
What was the date on that again?
1285 to 1347. So born 1285, died 1347. Okay. Other things that make science different than other endeavors is that any scientific theory, for example, or let's say a scientific experiment, okay, proofs should be able to be reproducible, okay? If I do an experiment and I say, oh my gosh, I discovered this cool thing when I did this experiment, right? It shouldn't be the case that I'm the only one that can do that experiment, right? Someone else should be able to take the same equipment, perform the same setup in the same way, and get the same results. You know, if I what normally happens? Like I pick something up and I drop it, right? And if I drop something, it falls, right? If I went into a room, closed the door, and I came out of the room and said, guys, I did this experiment. I picked up a pen and I went to drop the pen, and instead of the pen falling, the pen shot off towards the ceiling. And you're like, sure it did, okay? Show me, right? And I come out of the room and I try to reproduce the experiment. I go, look, watch. And it falls every time. It doesn't shoot off towards the ceiling, right? It's not reproducible. I very well there could have been some weird anomaly in the world that made that happen, but it's not a reproducible experiment, okay? Every experiment in science should be reproducible. In fact, there are some areas of science where that's difficult to do, specifically the areas of that deal with humans. Things like psychology and sociology actually have a lot of difficulty in reproducing some of the experiments that they and some of the outcomes that they achieve. But specifically things like physics, later today in a little while I'm going to show you guys something called the double slit experiment. It involves a laser and a very small little slit that the laser travels through, and you can actually see the light waves interfere with each other. Anyone can do that experiment, right? Anyone can go buy a laser, make tiny slits in a piece of paper, right, and perform that experiment. You guys can go home and do that experiment for dollars, okay? That's reproducible. So we say that's a scientific fact that things like, for example, in the double slit experiment, light behaves like a wave, okay, because I can reproduce that result. Okay. Nextly is that experiments should be falsifiable. Okay, this is one of the biggest things about science is that, so for example, many people tend to have like an innate distrust for scientific facts. Science says something is true, and you go, well, sure it is, right? Why should I believe you, right? We should tend to believe. I think we should tend to believe the scientific consensus, because the way people become well known in science is by disproving what theories that are thought to be proven correct, right? It's called falsifying things. So once somebody says something, like for example, 1905, Einstein comes out with the theory of special relativity, which we'll get to talk a little bit about, but it's the theory of light and how light works. If that was wrong, people would have jumped all over reasons why it's wrong. They would have done everything they can, then they did do everything they can to try to prove Einstein, in that case, wrong, okay? You're able to falsify it. You can do experiments that would disprove his theory, but every experiment that's done ends up backing up his theory, okay? So science will try to find the incorrectness, whatever's incorrect about whatever theory we want to say about our world. Scientific theories have to be able to be falsifiable. Okay, we have to be able to perform an experiment that could, in principle, disprove the experiment. Okay, if you can't do an experiment to disprove the result of some previous experiment, then the previous result is not falsifiable and it's not science. For example, religion says, it just doesn't matter which religion, I don't mean any specific religion, but religions say things like there is a God and God exists, right? Can you falsify that? Can you do an experiment to prove there is no such thing? No, right? It's not falsifiable, so it can't be science. I can say, no, there's not, right? There is no God. I can say that, right? But it's not falsifiable. I can't do any experiment to disprove that statement, right? So that statement is outside of the realm of science, and of course it's a religious statement, right? Based on, some people here may be religious. What's that based on? You say there is a God, and what, do you have any proof? Faith, right? It's faith. It's just faith. Okay, so faith is part of religion, which is different than science, right? Science puts no faith in anything. Science puts credence, belief in results, right? In identifiable, measurable results. Okay, the last two things that make science a bit different, and these are obvious ones: observation and measurability, right? Experiments should be able to have results that are observable. Um, any experiment should be able to have a result that's observable. If I can't, if I do an experiment and I say I discovered this amazing thing about the world, and you say show me, and you go, well, I can't. There's no way. I have no visible proof. I have no auditory proof. I've got no written proof, right? I've got no proof that the experiment was valid, right? Well, then I have nothing observable. I have nothing observable to show you. Okay, science needs observation. The results of experiments should be detectable by the human senses and amplified by special equipment and things like that, but detectable to the human senses. I can't see the radioactivity in this room, right? But there is. Okay, I can get out my Geiger counter and I can measure the radioactivity in this room, and I can observe the result. I can't see every little radioactive decay event, but I can look at my Geiger counter and it can tell me when there's a radioactive decay event. That's an observable result. And importantly, it's measurable, right? I can bring out the Geiger counter, I can turn it on for 1 minute, and I can measure the amount of radiation emitted from background radiation over that time. I can measure and quantify results. Radiography should satisfy all of these requirements. All right, so the next thing to say is, let's look at a couple of statements and try to decide which one is the most scientific. Okay, so there's 3 statements here. Statement number 1, the moon is made of green cheese. You guys ever heard that? The moon is made of cheese? Okay, so it's because it's got the holes in it. So number 2, intelligent life likely exists elsewhere in the universe. And number 3, Albert Einstein was the greatest physicist of the 20th century. Which one of these, or which of these are not, so let's just take falsifiability, okay? Which of these is not falsifiable?
1 and 3.
So, okay, so if I say the moon is made of green cheese, is there an experiment? Well, so being false and being falsifiable are different things, okay? We know the moon's not made of green cheese, right? Why do we know that? We've been there, right? We've been there. Stanley Kubrick did not make the moon landing film in his basement, okay? Okay, never mind. The moon is not made of green cheese, okay? It's a falsifiable statement, so it's a scientific statement, right? Okay, intelligent life exists elsewhere in the universe. Is that falsifiable? Can I, in principle, do an experiment to discover that? What would I have to do? I'd have to go everywhere, right? I'd have to go all the places in the universe. But so in practice, like actual going out and doing it, it's just not going to happen, right? There are places in the universe that are too far away for you to get to, right? Most of the places are too far away for you to get to. But importantly, in principle, it's a falsifiable statement. All I got to do is send people out in every single direction in the universe to go to every planet in the universe and look, right? Report back to me. That's falsifiable. So the first 2 are falsifiable, okay? Number 3, Albert Einstein is the greatest physicist of the 20th century. What do you guys think?
That's just someone's opinion.
Right. What was the very first thing that we, let's say it like this. Scientific endeavors are based in objective, observable evidence, right? Is there anything objective about saying that? Does anyone disagree that Albert Einstein was super duper smart? No, you don't disagree with that, right? Do you disagree that he invented several important theories about the world? No, he did those. He did those things. He invented several important theories about the world, general and special relativity, the photoelectric effect, which we'll talk about later. So he did some very important things, right? But there's no measurable way where I can say he is the greatest physicist of the 20th century. And by the way, he's important, but he's not the greatest. Okay, there are many others that are just as important, maybe even more. Okay, so scientific statements need to be falsifiable. Okay, so then next you talk about reproducibility, right? If I say the moon is made of green cheese and you go get a sample of the moon and bring it back and it's not green cheese, right? someone else can go reproduce that experiment. Someone else can go fly to the moon, go grab some moon rock and bring it back and show me, hey, this is not cheese, right? Okay. As well, I do the intelligent life exists elsewhere in the universe experiment. I send everybody out, they go look around, they come back, they go, there's nothing else. Sorry, we're the only ones. Okay. And it's reproducible because I can do it again. I can send more people out, right? So it's a reproducible experiment. There is nothing reproducible about the statement about Einstein being the greatest physicist of the 20th century because there's nothing to observe, there's nothing to measure, there's nothing to reproduce. And so that really gives us hopefully an idea about what we mean by, simple explanations that are reproduced, that we have reproducible results for, falsifiable, and the results are observable and measurable. Okay, that's what makes things science. So radiography includes a quantifiable amount of useful detail, right? We can say that an image has more or less information present. So a literal radiograph, may have more or less information there, right? We can change things to to add more or less information to our radiographic images. So there's a quantifiable amount of useful detail, a measurable amount of information, and all images have image qualities with regard to, things like our grayscale, amount of blackening or darkening on an image, the positions that we place patients in, so the type of information that we see based on patient position. We can quantify and measure our repeat rates, right? So the amount of repeated radiographs we perform. Everything we do in radiography is part of science because we can measure it, because we can observe results. Radiographers, it's our standard of practice to use common sense, sound judgment, be logically consistent. For example, I perform a radiograph on somebody, a chest x-ray on somebody, and then the next person that comes in for that same exam, who's the same size, I'm going to use the same, and for the new people may not know this, but I'm going to use the same technical factors, right? I'm going to use the same amount of radiation, the same type of radiation. I'm going to do everything the same because they're the same, effectively to me, they're the same thing, right? Two people, the same size, getting the same exam done. That's logical consistency, right? I'm not going to change things wildly from one person to the next just because I feel like it, right? I have a protocol I follow. So logical consistency, objective knowledge, and that is all done in a way to provide the best care possible for our patients.